Okay. So good morning, everyone. I would first like to thank the organizers for the opportunity to present my work here today. And again, my name is Aline Ramires. I'm currently a junior fellow at the Institute for Theoretical Studies at ETH in Zurich, more precisely until today. And on Monday, I start at the ICTP branch in São Paulo in the South American Institute for Fundamental Research within the University of the State of São Paulo. Also with a visiting position at the Max Planck Institute for the Physics of Complex Systems in Dresden for the year of 2019. And the work I'm going to tell you about today is about the concept of superconducting fitness, something that came out of my interactions with Manfred Sigrist at the Institute for Theoretical Physics, also at ETH, and with some more recent developments also in collaboration with Daniel Achterberg from the University of Wisconsin in the US. And most of what I'm telling you about today can be found in these three very recent publications. Oops. So if you haven't heard about this idea before and you hear the word fitness, you're wondering what I'm going to talk about, and maybe something like this comes to your mind. But I would like actually for you to think about fitness in a Darwinian sense, as you have seen the picture already, of the survival of the species which is better adapted to a given environment. And you might wonder, okay, how is that connected with condensed matter theory? The analogy I want you to keep in mind is the following. Instead of species, you could consider different superconducting order parameters, and as the environment, we can take the underlying electronic structure. To make it more concrete, for example, we know that a penguin would do very well in the Arctic, but probably not survive in the rainforest or in the Caatinga. This is an environment we find here in the northeast of Brazil. On the other hand, tatu-bola, an animal which actually lives here in the Caatinga, would probably not survive in the Arctic, but maybe could get along in the rainforest, who knows. So the idea is to have the parallel here. We have, in principle, different superconducting order parameters with different symmetries and qualitatively different band structures. So how can we quantify, give a measure of fitness of order parameters for a given electronic structure? So with this analogy in mind, I would like to take you over the outline of my talk. I will introduce the idea of superconducting fitness as we originally conceived it when we were thinking about the effects of external symmetry breaking fields in complex materials. And we are actually in the single band scenario, we recover something that is known as Anderson's theorems. But now we have a much more powerful tool to ask qualitatively the same kind of questions, but looking at complex systems, for example, strontium ruthenate, for which we are able to propose a phenomenological picture to understand the unusual behavior of the upper critical field in the system. Due to time constraints, I'm not going to talk about this. You can read in these two references, but I will focus on an upgraded version of this idea, which appears in a non-perturbative scheme in which we identify two functions, which we call the two fitness functions of A and Fc, which gives us a direct measure of compatibility and incompatibility of the gap and the underlying electronic structure. And to show you the power of this tool and its applicability, I will go to three different examples, very distinct examples. The first one, cerium platinum trisilicon, which is a non-centrosymmetric superconductor. The second one, potassium iron 2 arsenic 2, which is a hole-doped pnictide. And the last one, copper-doped bismuth selenide, doped topological insulator. So this idea of superconducting fitness really relies on two very robust ideas. The first one is BCS theory, meaning a weak coupling theory for superconductivity, which tells us that pairing is most effective for electrons which are at the Fermi surface with total momentum equals to 0. In this configuration, we get a logarithmically divergent susceptibility to the superconducting state, which is reflected in the form for the critical temperature, which is exponential in the coupling constant. I'm sorry. The other idea is more related to symmetries, what is known as Anderson's theorems. which really tells us what is the requirement to have the states at the Fermi surface that I would like to pair. So it essentially tells us that if we have time reversal symmetry, we can form a singlet, because if I have a state with momentum k and spin up, I'm guaranteed to have another state with momentum minus k and spin down. And analogously, for the triplet state, that symmetry is inversion. Now, one can go ahead and explicitly break these key symmetries, in which case the effect is essentially to split these originally doubly degenerate bands in such a way that I cannot form the desired pairs with total momentum equals to 0 anymore. And as a direct consequence of that, the critical temperature is reduced to the point that superconductivity can be completely suppressed if these fields are strong enough. So all of this is very well understood for this single band simple BCS scenario. The question is, do this picture still hold if we are interested in complex systems, or what kind of quantities do we need to look at to understand effects of symmetry breaking in complex materials? So to answer this question, I'll take you over an heuristic argument for the identification of this quantity, which really is based on this dichotomy between two different bases we like to work with. So if we think about superconductivity, we usually think in band bases and superconductivity as an instability out of a Fermi surface. But if we have a complex material, we usually start from the microscopics to construct a reliable model in which we can encode all the symmetry informations of the orbitals and the point group symmetry of my material. So let me start with this more reliable basis, the orbital basis, in which I can write a very general BDG Hamiltonian in terms of multi-orbital Nambu spinors here, with as many degrees of freedom as I need, which I label here from 1 to n, which can be different orbitals, or a layer degree of freedom, or a sublattice degree of freedom, and also the spin labeled as up and down. H0 is the non-interacting part of the Hamiltonian, which in this basis is generally not diagonal. There will be interorbital hopping, spin-orbit coupling, and the like. But there will always be a unitary transformation which diagonalizes this matrix, H0, and takes us to the band basis. Now, one can go ahead and rotate also the order parameter to this new basis, the band basis, in which case it can be written as so, with the subtlety on the transformation, because the Hamiltonian and the gap connect different spaces. Now, in presence of both time reversal and inversion symmetry, we know that the spectrum is going to be doubly degenerate. So on top of being diagonal, this Hamiltonian in the band basis will come with 2 by 2 blocks proportional to the identity, right? And in case I want to guarantee that I have a weak coupling stability, I would rather look at intraband pairing as a leading pairing for my instability. In such a case, we also have that this object, the gap matrix in the band basis, is also block diagonal. And under these two conditions, which I would call the optimal pairing condition, we have that these two objects rather trivially commute. So this we found in the band basis, the basis we like to think about superconductivity. But what does this give us in the orbital basis? It gives us this. We can use the unitary transformation backwards to find this slightly modified commutator, where in the second term we need to take complex conjugate and k to minus k. So if this condition holds, we have this optimal pairing condition. But in general, I can evaluate this quantity, and it won't be equal to 0. It will be equal to something finite. So actually, we baptize it as superconducting fitness. We call it superconducting fitness and label it as FC, C because it resembles a commutator. And it really gives us a measure of the incompatibility of the gap and the underlying electronic structure. Again, if it's 0, I have the optimal pairing condition, meaning order parameter and electronic structure are compatible. And if it's finite, it means there is something detrimental in the underlying electronic structure for this specific order parameter I'm evaluating here. So to benchmark this quantity with things we know very well, I'll take you back to the trivial case of a single band superconductor. And the order parameter can be either a singlet or a triplet. And I will introduce to H naught, which in this case is something trivial, just a dispersion proportional to the identity. I'll add to that either a term which breaks explicit time reversal by a Zeeman term, or a term which breaks inversion symmetry, something that looks like a Rashba type spin-orbit coupling. And I will evaluate this function for all these cases. And what I find is the following. For a singlet state, time reversal symmetry breaking is always detrimental to superconductivity for a magnetic field in any direction. Inversion symmetry breaking is not detrimental for a singlet state, while for a triplet, things get a bit more subtle, in the sense now where we have a extra directionality to the order parameter, given in terms of this D vector, in which case the magnetic field is detrimental only if it has a component in the same direction as the D vector. And for this inversion symmetry breaking case, it's detrimental only if the associated Rashba vector has a component perpendicular to it. So I'm not telling you anything new with this table. This is things that we all understand very well. But I'm giving you a unified framework to answer this question: what are detrimental effects to superconductors? And on top of that, within the standard weak coupling assumptions, we can find this nice closed form equation for the effects on the critical temperature, which is given just in terms of the unperturbed critical temperature and the average over the Fermi surface of this fitness function Fc, and some universal numbers here. So I believe this is a very neat framework which allows you to write such nice closed form equations, but now we can use as a tool really to look at a more complicated scenarios. But before I go to the examples, I would like to present you an upgraded version of this idea where we identify the second fitness function Fa. So to start with that, I again start with a Hamiltonian in the orbital basis, which now I parameterize by a series of functions, H, A, B, that depends on momentum, where A takes into account the orbital degree of freedom, and B, the spin degree of freedom. And for minimal multi-orbital model, we have a two-orbital model, and tau and sigma here are just Pauli matrices. So in principle, for the most general Hermitian Hamiltonian, we have 16 of such parameters, what looks like a lot for a two-orbital problem. But in presence, again, of both time reversal and inversion symmetry, the set of 6 parameters is drastically reduced to just 5 plus the identity, what is quite nice. And really doesn't depend what's the character of these orbitals. They can have same parity, different parity, or be associated with a sublattice structure. The subset of 5 matrices that you're left over with, they always form a totally anti-commuting subset, which looks very much like Pauli matrices. So with this in hand, and remembering that again, in presence of both of these key symmetries, my spectrum is doubly degenerate, I can reparameterize my problem in a smarter way in terms of the C vector dotted with the array of these 5 matrices I'm left over with. So I know that my Green's functions will have just 2 poles, which with energies given in terms of these parameters. So without going too much detail, one can plug in this parameterization of the Green's functions into the gap equation, and then after some manipulation, we find this very suggestive form. So in the first term, we have Green's functions which come in with poles in the same bands, meaning we find essentially what is we know already from BCS theory. We have intra-band pairing here. We'll find the standard Cooper logarithm, what guarantees the robustness of the superconducting stability, meaning I'll find superconductivity even for an arbitrarily small attractive interaction in this case. And this term comes weighted by the trace of the square of this new fitness function Fa, with the A, of course, related to the fact that it's the anti-commutator version of the previously defined quantity. So we associate this function with a measure of robustness of the superconducting stability. The second term, which comes with Green's functions with poles in different bands, comes weighted by the trace of the square of the FC function, which I presented to you before. And we already know that this gives us a measure of incompatibility, or tells us that there is something detrimental in my normal state Hamiltonian. Again, we are able to find a closed form equation for TC in this case, which really highlights the role of each of these functions more explicitly. So we find something that looks like the BCS critical temperature, with now here the strength of the interaction in a given channel, weighted by this parameter alpha, which usually just the density of states, but now it's the density of states with this important form factor, which is average over the Fermi surface, which is the trace of the FA function squared, meaning if this function is equal to 0, you don't get a weak coupling stability. Now, there is a second exponential factor here with a parameter delta, which depends on the fact that FC is finite, which will always reduce TC from its optimal possible value. What again makes clear that the finiteness of FC gives us a measure of detrimental effects. So with these two functions in hand, now we understand what's their role. Let's look at the examples. The first example is a one-band model, cerium platinum silicon. It's, as I mentioned in the beginning, a non-centrosymmetric superconductor. Therefore, we have a Rashba type spin orbit coupling of this form with a G vector here. And given the point group symmetry, I can enumerate all the symmetry allowed order parameters. Here I focus just on the triplet states. And this figure is from previous works where they give the behavior of TC as one cranks up the value of the spin orbit coupling. So I want to show you how looking now at these functions can give us a lot of intuition and a lot of the qualitative behavior you would get by completely solving the problem numerically. So first, let's look at FC. And we see that it's usually finite once we turn on spin orbit coupling. This is already averaged over a spherical Fermi surface. And there's something interesting here. Just the order parameter in the A2 channel has 0 FC, meaning it's the only one which is robust once I turn on spin orbit coupling, while all the other ones have a finite FC, therefore they are going to be suppressed sooner or later. Now, to understand the different rates of suppression, we can look at the second fitness function, FA, and we find again interesting things. For example, the first two order parameters in the A1 representation have 0 FA, so meaning they don't even have a weak coupling stability anymore, therefore they will be very quickly suppressed. The third one in the same channel have always a finite FA, therefore there's this tail here telling me there is always a finite TC, even though it will be very, very small, because I have the guarantee of the weak coupling stability by the fact that FA is finite. The other order parameters in the B and E channels have something interesting, that FC is equal to FA, meaning they are a bit more robust, and that's why they are suppressed, but at a much lower fashion, because at the same time that this term suppresses superconductivity, this actually enhances, has the tendency to support it. So perhaps one of the messages of this example is that spin orbit coupling would suppress all superconducting order parameters, but the one in the A2 channel. Now I want to show you a contrasting example, which is potassium iron 2 arsenic 2. This can be modeled by a minimal model with two orbitals of same parity in this basis. And I'll use the parameterization I introduced to you a few slides ago, where here the parameters and their momentum dependence are given explicitly. And it was recently proposed by Oskar Wafek and Andrei Chupukov that the A2 channel in this material is naturally attractive if the Hans coupling is larger than interorbital Hubbard U. And the order parameter in this channel looks like this. But when you diagonalize this problem and look at this order parameter, you find that actually it's of interband character, meaning even if the attractive interaction will need to be strong enough to overcome this interband gap, what doesn't look very promising. And in our language, it means that the fitness function of A is equal to 0. Now, interestingly enough, we can introduce spin-orbit coupling, or the 2-3 term to this Hamiltonian. And then we find, interestingly enough, that this term is the only one which supports a weak coupling stability in this material. So here, the spin-orbit coupling has exactly the opposite role that it had in the previous example. It actually guarantees a weak coupling stability in the A2 channel for this material. And as a last example, I'd like to take you over copper-doped bismuth selenide. It's also described by a minimal two-orbital model, now with opposite parity. The Hamiltonian can be parametrized in the same manner, with all the symmetry-allowed terms listed here, their expansion around the gamma point, their magnitude around the Fermi surface, and what's their character. And given the point group, again, one can classify all the symmetry-allowed order parameters, their character, and their form in this basis. So, interestingly enough, all these parameters have more or less the same magnitude at the Fermi surface. So what I'm going to do in this table is to pick from here the terms that contribute to a finite FC, listed in this column, and terms that contribute to a finite FA, listed in the second column. And with that, we can start making some statements. For example, the order parameter which seems to be the most robust is this first one in the A1G channel, but it seems to be a rather trivial one, not very exotic. It's just an intra-orbital singlet state. And it's the most robust because most of the terms in the Hamiltonian contribute to FA and none contribute to a finite FC. And the least stable is actually the second order parameter in the same symmetry channel, where just one of these terms in the Hamiltonian give you a finite FA, and actually many of them contribute to a finite FC. But it was already pointed out by Liang Fu and Edis Berg a few years ago that the interesting, oh, sorry for that, that should be down. The interesting order parameters in this material are the ones with odd parity because they are naturally topological given the Fermi surface location, the location of the Fermi surface in this material. So if you would like to favor states which are of this character, we can look more carefully at the role of each of the symmetry-allowed terms in the Hamiltonian and how they support or suppress my superconducting state. For example, we can look at spin-orbit coupling, the 1,1 and 1,2 terms in my Hamiltonian, and then we see that they mostly support these odd superconducting states, but they also suppress the ones in the A1 representation. Another statement one can make is looking at the 3,0 term, which gives a measure of the imbalance of intra-orbital hopping within orbital 1 and within orbital 2. This term is actually detrimental to all odd order parameters. So if we could tune this material in a way to suppress this 3-0 term, perhaps is a good way to favor some exotic order parameter, in particular this one in the A1U channel, which has only this 3-0 term as something detrimental to it. So with that, I would like to conclude saying that this concept of superconducting fitness and these two functions we are able to identify, they seem to be a very useful tool to start thinking about engineering the normal state Hamiltonians in order to favor your exotic or topological superconducting state. And again, it seems to be a very cheap tool, but at the same time, it allows us to encode all the important symmetry aspects of the problem concerning the properties of these effective degrees of freedom and the underlying symmetries of the lattice very, very carefully, and to account for all possible symmetry allowed terms in the Hamiltonian and all possible symmetry allowed order parameters. And as perspectives, I believe, and I already have been working on some of these aspects, this structure, meaning these functions will appear also if we look at the effects of impurities in complex systems or problems in interfaces, and something that I haven't told you a word about, interactions. That's something that I'm cooking up, and perhaps in the next opportunity I'll be able to tell you more about. And with that, I'll thank you for your attention.